This is GPT-4, 1.8 trillion parameters. To run it, you need a data center the size of a football field, drawing enough electricity to power a small town. Now look at this. A language model running on your phone. No internet, no cloud, no data center. Same intelligence, fits in your pocket. How is that possible? How do you take a model that needs a $100 million server farm and shrink it to run on a device that costs a few $100? That's what this video is about. The art and science of model optimization. The techniques that are democratizing AI, one compression trick at a time. Today, we're going deep into 3 pillars. Knowledge distillation, teaching small models to think like big ones. Quantization, the precision trade-off that changes everything. And pruning, performing surgery on neural networks to cut the fat without losing the brain. Here's the problem no one talks about. Language models are getting bigger at an absurd rate. In 2018, BERT had 340 million parameters. That was considered large. In 2019, GPT-2 had 1.5 billion. 2020, GPT-3 exploded to 175 billion. And by 2023, GPT-4 hit an estimated 1.8 trillion. That's a 5,000-fold increase in just 5 years. Like going from a bicycle to a Boeing 747. But here's the uncomfortable question nobody asks. Do we need all those parameters? Research shows that up to 90% of a large model's parameters are redundant for any specific task. That's like hiring 10,000 employees when you really only need 1,000. Most of those neurons, they're basically sleeping during inference. So today, we'll learn 4 battle-tested techniques to shrink these giants without losing their intelligence. Distillation, quantization, pruning, and efficient architecture design. By the end, you'll understand exactly how to fit a genius inside a phone. Imagine you have a brilliant professor, decades of experience, encyclopedic knowledge, but they charge $1,000 an hour. What if you could have them teach a younger, cheaper tutor, and the tutor becomes almost as good? That's knowledge distillation, published by Geoffrey Hinton in 2015. The idea is deceptively simple, but the results are extraordinary. Step 1. Take your massive teacher model, say BERT large with 340 million parameters, and run it on your training data. But here's the key. Instead of looking at just the final answer, you capture the model's soft predictions. The full probability distribution. See these soft probabilities? The teacher doesn't just say it's a cat. It says it's probably a cat, but it looks a bit like a dog and maybe a tiny bit like a fox. That uncertainty, those secondary predictions, they contain what Hinton calls dark knowledge. Information that's invisible in the hard labels, but incredibly valuable for learning. Step 2. Train a much smaller student model, say just 66 million parameters, to match those soft predictions. Not the hard, binary answers. The soft, uncertain, nuanced ones. The student learns not just what the teacher thinks, but how the teacher thinks. Step 3. Temperature scaling. By dividing the model's output logits by a temperature parameter, typically between 2 and 20, we soften the probability distribution even further. Like turning up the heat on invisible ink, this reveals hidden patterns in the teacher's knowledge. The result? DistilBERT, a student model with 40% fewer parameters, retains 97% of BERT's performance. 40% smaller, 60% faster, but practically just as smart. When you use a language model on your phone, you're almost certainly talking to a distilled model. The full model is too expensive, even for the biggest tech companies. Here's mind-bending fact number 2. Every single number in a neural network is stored as a 32-bit floating point number. That's 32 ones and zeros, giving you extreme mathematical precision. But do you actually need that precision? If a weight is 10.0000000001, does that last decimal place even matter? Quantization says no. We can use fewer bits. 32 bits down to 16 bits. That's half the memory right there, with almost zero quality loss. Like switching from a 4K photo to 1080p. Can you really see the difference? Go further. 16-bit down to 8-bit integers. Now we're using 4 times less memory. The model runs 4 times faster. And the accuracy drops, just 1 or 2%. For most real-world applications, that's completely acceptable. And then there's the nuclear option, 4-bit quantization. This is where researchers in 2023 shocked the entire AI world. A 65 billion parameter model, quantized to 4 bits, fits on a single consumer GPU. A model that normally needs a $100,000 server cluster, running on a $500 graphics card. Let that sink in. Modern techniques like GPTQ and AWQ achieve this by being smart about which weights to compress. Not all weights are equally important. These algorithms identify the critical weights, the ones that carry the most information, and preserve them while aggressively compressing the rest. Here's the practical trade-off tree. Full 32-bit precision, maximum quality, maximum cost. 16-bit, twice the speed, negligible quality loss. 8-bit integer, 4 times the speed, 1 to 2% quality drop. And 4-bit, 8 times the speed, 3 to 5% drop, the sweet spot for real-world deployment. If distillation is teaching and quantization is compressing, pruning is surgery. Literally cutting out parts of the neural network that don't contribute. The lottery ticket hypothesis, one of the most beautiful ideas in deep learning, says that inside every large network, there's a tiny subnetwork that does all the heavy lifting. The rest? Dead weight. Like finding a winning lottery ticket hidden inside a stack of millions. Structured pruning takes this further. It removes entire neurons, entire attention heads, even whole layers. In BERT, researchers found that up to 40% of attention heads can be flat out removed with barely any impact on performance. 40% of the fancy attention mechanisms? Completely redundant. Then there are efficient architectures designed from the ground up to be small and powerful. Mobile BERT, 4.3 times smaller, 5.5 times faster. Tiny BERT, 7.5 times smaller, 9.4 times faster. Albert uses cross-layer parameter sharing. The same parameters are reused across layers, dramatically reducing the model's total size without losing capacity. And the bleeding-edge technique that's taken the field by storm, LoRa, low-rank adaptation. Instead of fine-tuning all the parameters in a massive model, you freeze the original weights and add tiny adapter matrices, trainable modules that slot into specific layers. You end up fine-tuning less than 1% of the parameters, achieving 97% of full fine-tuning performance. This is how most people customize large language models today. Everything I've shown you sounds like a miracle. Smaller, faster, cheaper. What's not to love? But here's what nobody tells you. Problem 1, bias amplification. When you compress a model, you don't shrink all capabilities equally. The model retains performance on common patterns, things it saw millions of times during training, and loses performance on rare ones. Minority languages, unusual dialects, underrepresented groups. This means a medical AI that works perfectly in English might fail catastrophically in Swahili. And compression makes this gap wider. We're not just compressing models. We might be compressing away fairness. Problem 2, the accuracy cliff. Quantization works beautifully, until it doesn't. Push below 4 bits, and suddenly the model falls off an absolute cliff. Not a gentle decline, a catastrophic collapse. Like removing bolts from a bridge. Take out 50%, fine. Take out 90%, somehow still fine. Take out 91%. The entire bridge collapses into the river. Problem 3, catastrophic task forgetting. Pruned and distilled models often lose capabilities in completely unpredictable ways. The model might ace your benchmark tests, text classification, sentiment analysis, all green check marks, but completely forget how to do something you haven't tested. Like translation, or code generation, or handling sarcasm. And the deepest problem of all, we don't fully understand why these techniques work as well as they do. The lottery ticket hypothesis is beautiful, but we can't reliably predict which tickets will win. Every deployment is fundamentally a gamble. You compress, test on your benchmarks, deploy, and pray that the specific capability your users need wasn't in the 90% you threw away. So where does this leave us? Let me give you the practical decision framework. Deploying to mobile or edge devices. Start with quantization. 8-bit integers give you 4 times speed up with minimal quality loss. Need a permanently smaller model for production? Knowledge distillation. Train the student once, deploy forever. 40% smaller, 60% faster, 97% of the quality. Fine-tuning a large model on limited hardware? LoRa is your answer. Adapt the giant without needing to download or store the giant. Less than 1% of the parameters, almost all of the performance. Running AI on a GPU budget? 4-bit quantization with GPTQ. Fit a 70 billion parameter model on a single gaming GPU. Need maximum compression? Combine everything. Distill, quantize, then prune. Stack the techniques for compound savings. Now here's the stat that puts it all in perspective. LLaMA 270B, a model that normally requires 4 A100 GPUs costing $40,000, can be quantized to 4-bit and run on a single RTX 4090, a $1,500 consumer card. That's a 96% cost reduction with less than 5% quality loss. The future of AI isn't just about building bigger models. It's about making the models we have accessible to everyone. Imagine a medical AI running offline in a rural clinic with no internet, a translation model working on a refugee's phone, an educational tutor running on a 5-year-old laptop. That is what optimization makes possible. Next up, the final video of Unit 3, NLP applications, where we see all of these techniques come together in the real world. If you want to run AI on your device, hit subscribe and the bell icon. Drop a comment. What's the smallest device you'd want to run a language model on? A smartwatch? A toaster? I genuinely want to know. See you in the next one.